In general, a phase diagram is a three-dimensional plot of the pressure versus the molar or mass specific volume versus the absolute temperature. For this reason, the phase diagram is sometimes also called the PVT diagram. The phase diagram is hence a three-dimensional surface that defines the allowed P, V and T values that a substance can have. We can obtain the phase diagram for an ideal gas by using the ideal gas equation. This can be done by fixing one of the three independent variables in the ideal gas equation, varying a second one, and using the ideal gas equation to solve for the third one. For example, we can fix the temperature T, vary the molar specific volume V sub capital M, and then use the ideal gas equation to solve for the pressure P. This would give us a P versus V sub capital M curve at the value of T that we selected. We can then repeat this process to obtain other P versus V sub capital M curves at other values of T. Finally, we can combine these curves to form a PVT solution surface for the ideal gas equation. It should be noted that the three-dimensional surface that is obtained by plotting the ideal gas equation using the molar specific volume is the same for all gases that obey the ideal gas law. If on the other hand the mass specific volume is used, the plot that is obtained would be specific for the gas whose gas constant is used. A simplified two-dimensional plot that is often used instead of the PVT surface plot is the PV diagram, which can be plotted at single or multiple temperatures. Shown here is a PV diagram for an ideal gas at 5 values of the absolute temperature T. Any curve of constant temperature on the PV diagram is called an isotherm, and so we have an isotherm at T equals 200 Kelvin, 400, 600, 800, and 1000. As can be seen from the ideal gas equation, if the temperature is constant, then the pressure is inversely proportional to the specific volume. As opposed to an ideal gas that always remains in a gaseous state, real substances undergo a phase change into the liquid or solid forms at low enough temperatures and high enough densities. Since the density is equal to the inverse of the mass-specific volume, we conclude that substances exhibit a behavior that closely mimics that of an ideal gas at high temperatures and high values of the specific volume. Thus the behavior of hot rarefied gases can't be described by the ideal gas equation without introducing much error into our calculations. However, as the temperature decreases, and the specific volume decreases, or in other words the gas becomes compressed, the behavior of the substance deviates more and more from the ideal gas equation. At some point we can no longer use the ideal gas equation to describe the behavior of the substance. We then have to rely on the actual PVT plot of the substance that shows under which conditions specific gaseous, liquid and solid phases of the substance occur. Shown here is the phase diagram of a substance that contracts on freezing, which is the typical behavior of most substances. The three-dimensional surface of the phase diagram is a function of the pressure, P, the specific volume, V, and the temperature, T. The two-dimensional pressure versus specific volume plot on the left is a projection of the three-dimensional phase diagram on a plane that is perpendicular to the temperature axis. The 2D plot shows several temperature isotherms, or curves of constant temperature. Each isotherm corresponds to a curve that forms at the intersection between the plane that is perpendicular to the t-axis at a given temperature value, and the surface of the 3D phase diagram. At different temperature values, we get the different isotherms that we can see on the two-dimensional plot that correspond to the intersection of constant temperature planes with the surface of the three-dimensional phase diagram, such as this curve in the gaseous region, and this curve also in the gaseous region, this curve at the critical temperature, this curve that passes through the liquid vapor region, and this curve that passes through the solid vapor region. We can see on the phase diagram the part of the surface of the plot that corresponds to the substance being in a gaseous state, a liquid state, a vapor state, a solid state, a liquid vapor mixture state, a solid liquid mixture state, and a solid vapor mixture state. There are two important features to know on the graph: the critical point, which is located at the intersection of the liquid region with the vapor region, and the triple line, which is located at the intersection of the liquid vapor mixture region and the solid vapor mixture region. The liquid, vapor, and solid phases can all exist in equilibrium on the triple line. In the gas region of the phase diagram, the further away the condition of the substance is from the liquid and vapor regions, the more the substance behaves like an ideal gas. As we have mentioned previously, behavior that mimics that of an ideal gas occurs when the temperature and specific volume are both high. This is evident by comparing the shape of the highest value isotherm that is shown on the real substance phase diagram with that of an ideal gas isotherm, as shown here in the 2D plot of the phase diagram for an ideal gas.